Hi, it's time for another math easy solution. To discuss further into calculus with parametric curves and look further at the tangent series and continue on the example 1 and go over part 3 of it. In my earlier videos I went over part 1 and 2, which were dealing with part A and B of this example question. But now in this video I'll go over part C and D in this third part. And again, recall the example states a curve C is defined by the parametric equations x equals to t squared and y equals to t cubed minus 3t. And then from the first part of the question, I showed that there was two tangents at the point 3, 0. And then part B, I showed that I showed the points where the tangent is horizontal and the other time where it's vertical. And now part C, it says determine where the curve is concave upward or downward, and then part D is put all the parts together and then sketch the curve. So let's look at part C, and now we can solve this by the second derivative test. So if we recall the second derivative test, test here, and you can see the proof for this and more explanation on this in my earlier video, and I'll put that in the video description below, so check that out. So basically the idea is to just find where the second derivative is either positive or negative. So the second derivative in our case, d squared, or I'm basically writing the second derivative like this, d2 y and then d over dx squared like that equals to, this is the same thing as writing d over dx of, well, dy over dx. This is just basically taking the derivative of dy over dx, so you do it twice. And now we could plug this inside, and like I've gone over in my earlier video, on the first video on the tangent series, what we end up getting is with parametric curves, this is the same as writing d over dt of dy over dx as a second derivative, because we would just throw this dy over dx inside where the y used to be. And now we have this dx over dt is the bottom. So the ratio of dy over dt is the derivative, but we're doing it twice, so we throw this inside. So again, make sure to watch my earlier video, put that in the video description below. So we have this scenario, and now recall from my earlier video. So recall from part A or part 1 where I showed, and you could see this here, let's go to part 1. So click this here, and I showed that the slope in this particular example, dy over dx equals to this, etc., and I solved it, and it equals to 3t squared minus 3, and then over 2t, like that. So write that down. We have dy over dx, so we want to throw that inside this area here. This equals to 3t squared minus 3 over 2t. And now we could simplify this even further by factoring out this 3. So we have a 3 over 2, and then we have this t here, and then we have t squared minus 1, like that. And we could divide the t inside so that we end up getting, we end up getting 3 over 2, and then just divide this inside to make it easier to take the derivative of it again. So what we get is, this becomes t minus, and now this is a 1 over t, like that. So now this is our dy over dx, so we could throw this all inside here. So we have d2 y over dx squared equals 2, and then now we could plug that in. So d over dt of this right here, 3 over 2 t minus, and then this one I'll make it easier to take the derivative, put a t to the negative 1 like that, and then over dx over dt, which is the same thing as taking derivative of this x equals to t squared. So this means we have d over dt of t squared. So then now we just take the derivative. The top's going to be, well, 3 over 2 times the biderivative of t is just 1. And then minus, and we bring this negative 1 down, it becomes positive 1, and then we subtract the power, so we'll have it as t to the negative 2, like that. Over at the bottom is going to be 2t. And now what we'll do is just try to simplify this even further. So then there's a 3 over 2, and there's a 2 there. We can combine the 2's into 4, so we have 3 over 4 times it by here. This is going to be now, well, we have a t, and then we have over here 1 and then plus 1 over t squared, like that. So here I'm going to multiply this by t squared over t squared. Over t squared, like that, just so we have a common denominator of t squared, and then we can add those up. This equals to 3 over 4, and then we have this t here, so then this becomes t squared, and then so t squared plus 1. We'll put this like this: t squared plus 1 over t squared, like that. And then we can combine this t with here, so we finally get, and the reason we're simplifying is to make it easier to determine whether the second derivative is positive or negative. So what we get now is 3 over 4 times it by, and now we have this t squared, plus 1, and then we have at the bottom, well, this t cubed, like that. So then this is now our second derivative, like this. And again, you could write this as y double prime, like that. So let's put it like that. So now that we have this, we have to determine if it's positive or negative for different values of t, and that's based on the second derivative test. And what we'll notice is, note that if we take everything but the t cubed, we have 3 over 4 t squared plus 1. Well, this one is always positive. Whatever value of t, we always have positive, and there's only just plus values in 3 or 4. So this is greater than 0 always. And also now what we have noticed is that the only thing that can change signs is a t cubed. So t cubed is greater than 0 if, well, t is greater than 0. And also t cubed is less than 0 when you have a negative number. So if t is less than 0, right? This neater. Yeah, so then when this is negative, the whole thing becomes negative because this is already always positive there. So what this means is now we can apply the second derivative test. So thus y double prime, which equals to, well, d squared y, and then dx squared, just write it like that notation. This is less than 0, or I'll actually write it different. So this is greater than 0 if t is greater than 0. So when this is greater than 0, when this whole thing is greater than 0, what we have is a concave upward, because you could consider this as the acceleration. So the curve is accelerating and it's increasing towards the y direction. So concave upwards. And likewise, y double prime is less than 0 if t is negative, if t is less than 0, like that. And this is at concave downwards. Yeah, downwards, like that. So now that we know that it's concave downwards and upwards at basically when t is negative, concave downwards, and t is positive, concave upwards. Yeah, so the next step now is to, well, graph this whole parametric equation set. So sketch the curve. We'll do that, and we will recall what we did in my earlier videos. So this is part D. Let's just graph this out now. So the graph looks something like this. We draw x and y coordinates like that. So what we know is, that at let's go here. If this is 1, 2, 3. So at this point, if I recall from the first part right here, this is part 1. I showed, so just scroll here. I showed that at this point we have two tangents. At this point, this is at 3 and 0, like that. And yes, so make sure to watch that earlier video for proof of that. So then at this point here, we have two tangents. Yeah, we have two tangents right here at 3, 0. And I'll draw this in red just to signal it's a tangent line like that. And then it's tangent line crisscross like that. And now from the second part, if I go there, the second part right here, what I've shown is that from the second part, I'll scroll down here. So again, from here, this is the second part. I showed that we have 1, 2, and 1, negative 2. We have horizontal tangents, and then there's vertical tangents here, horizontal at those areas right here. And at these points over here, when we have the negative y, this is when we plugged in plus t. So when we plug in plus 1 as t, we get the -2. So then this area right here, this is at t is equal to plus 1. Here it was at t equals to -1, like that. Just so we know the direction. So if we go back here, so what we have now is at point, this is 1, this is 2, let's say this is 1, -1, this is -2. So at this point here is our, this is the point 1 and -2. And now we have at this point, this is our point 1 and plus 2, like that. And then at the origin is the vertical asymptote. This is, I'll just put the 0 like that. Here, this is the origin. Yeah, so we have a vertical asymptote here. We have a horizontal asymptote here. Horizontal asymptote here in red. And again, this is at t is equal to, remember this was when it's positive, we have t is -1. This was at t equals to plus 1, like that. Or just write it as 1. So this is at t equals to 1. Yeah, so this means since we've set up from now this part of the equation concave downwards when it's t is negative, but concave upwards when it's positive. So then we've established that it's adherent to assume it's all continuous, which it actually is. So we have at this point right here, this is concave downwards because we have t is negative, and then t is positive at this point, it's going to be concave upwards like that. So now if we were to graph it, we would, if we were starting off from a negative area, then reaching, then eventually going positive, we would, let's say, start over, let's draw it like this kind of. So we have a graph that's curving around downwards because it's concave. On this side is going to go like this, and then, yeah, so basically tangent line across there, so we have a curve like that. And then across here, it goes to a flat surface, concaving upwards, and then basically crisscrossing like that. I'll draw this one a bit better. This is a bit hard to graph. So yeah, it just basically aligns it across like that. And then on this side, reaching it all the way down. And it's a curve like that, just make this a bit smoother. So that's how it looks like. And since this is the negative area reaching towards a positive, we would just assume that it's the arrow is directing as t increases. So it's going like this. It's looping around like a knot like that. And here what I've done is I've just graphed it using that Desmos calculator that I've been doing many times in my earlier videos, just to show you that that's in fact how the shape looks like. And you can click here. It's a pretty cool calculator. I just saved it for you guys. So you can go here, and what I've done is I've plotted this as parametric curves, t squared, and you have t cubed minus 3t. I've also done it twice here, and you could show label, just so that but then change a variable to a so that we could play around with this. As you can see, it moves like that. So as you start off from, this is going backwards now, which is pretty amazing. So as you start off from, let's say, the negative, and then as it increases, it's going toward, just a way to slow it down. So as you can see, it's going around the direction as t is increasing. In this case, a is the same as t, just to do that, which is quite amazing. And this is from -3 I have all the way to 3 like that. Let's just speed this up. I made this go all the way to 2.5. Let's see where it stops. Yeah, it stops halfway there. And it was pretty cool. So this is this is confirmation for how our curve looks like, and I highly recommend playing around with this calculator. It's quite amazing. Anyways, that is all for today. Here's the link to it. You can click it. You can download these notes and click that link and play around with the graphs. Quite amazing. Anyways, that's all for today. If you'll learn and enjoy. It's quite interesting video on curve sketching using calculus and with parametric curves. Hopefully you enjoyed, and like always, you can download these exact notes and link below. And thanks for watching, and stay tuned for another Math Easy solution.